We are Team V, the essence, circuit, design, and fabrication for 3U CubeSat, and this is our Capstone project. Our team is made up of 2 electrical engineering students, Abel Bayen and Syed Abidi, and 2 space engineering students, Gabriel Kinelli and Tej Patel. During the last 2 semesters, the members were working as part of the electrical team for York University's Essence satellite. Essence, funded by the Canadian Space Agency under the Canadian CubeSat project, aims to design, manufacture, and launch a 3U CubeSat into low Earth orbit. But what exactly is a CubeSat? It is a 10 by 10 centimeter satellite, referred to as 1U, and can have multiple 1U satellites assembled, such as in the 3U design of our project. The 3U CubeSat holds all mission-critical components for the roughly 1-year lifetime, such as the onboard computer, solar panels, and batteries. However, custom printed circuit boards, or PCBs, are needed to house certain components which cannot be directly integrated into the satellite through a pre-made PCB. This includes the optical camera and proton detector payloads, as well as the attitude control system, to name a few. Our team's goal was to design 4 of 9 total PCBs, housing these important components for the Essence mission. One major circuit on these boards involved initializing a 30-minute startup timer, required once released from the International Space Station by the company NanoRacks. In the following presentation, the team will outline our work, which involved the electrical schematic and PCB layout design, prototype testing, and procurement of the final product currently underway.
To capture images of the northern permafrost, the CubeSat hosts a special nano-immersive, high-resolution camera made by Canadensis Aerospace Corporation. The camera is radiation tolerant and operates under vacuum-like conditions. That makes it ideal for use in low Earth orbit. It has an image resolution of 4000 by 3000 pixels, onboard storage of 64 gigabytes, and operates at 3.3 to 5 volts. The camera is mounted on board 1. Despite many of these attractive properties, however, the device is nonetheless non-standard, and so isn't available as part of an off-the-shelf PCB. Furthermore, the camera's data transmission uses a fairly non-common RS-422 interface, which requires extra circuitry for processing and conversion to SPI. CubeSats are deployed into low Earth orbit by NanoRacks, a satellite launch service company based in Texas. They carry satellites into space via a shuttle to the ISS and are then released via a device referred to as the NanoRacks CubeSats deployer. To use their service, NanoRacks imposes strict requirements on third-party satellites that ensure high standards of safety and reliability. One of these requirements is that the CubeSat power system remains disabled for a minimum of 30 minutes after deployment, but no more than 35. This requirement ensures that, after deployment, none of the CubeSat's electrical equipment interferes with the deployer. Once released from the ISS, the CubeSat must have the ability to count down from 30 minutes, at which point it activates the power subsystems. Sensor data from all board equipment is transmitted to and processed by 2 Arduino Pro Minis situated on board 6. The Arduinos gather data from a collection of sensors measuring a range of phenomena, such as luminosity, temperature, and CubeSat orientation. Once the data is processed, it's sent to the onboard controller on board 5, which is responsible for the overall operation of the spacecraft. The onboard controller monitors all subsystems aboard the CubeSat and executes commands received from the ground station.
The main aim of Board 9 is to connect the reaction wheel and the optical gyroscope to the rest of CubeSat. In general, it acts as an interface for these components. For instance, one of the main aims of the Essence project is to observe the snow and ice covering of northern Canada. The gyroscope will send positional data of CubeSat to the controller, and the controller controls the reaction wheel to align the camera properly according to that information. The controller itself is the Arduino, which is on board 6, but the information between these components is relayed through board 9.
Here you see an image of the schematic for board 1. The camera's D-sub connector is mounted here, and its signals are routed through 2 main circuits. The first functions as an analog to digital type converter for the temperature sensing data, while the second converts RS-422 to SPI, where it's then routed to board 6. The timer circuit schematic consists of 4 main sub-circuits. The first 2 are the timers themselves, RC circuits whose time constant aligns with our 30-minute requirement. At approximately 1800 seconds, the output is pulled high to VBAT. 2 timers are used for redundancy. The output is then passed through a multiplexer to what's referred to as a latching circuit. Here, a floating wire that drives a so-called kill switch is pulled to ground, and that activates the NanoPower P60 dock unit and powers the entire satellite.
The board 9 is essentially a bunch of connectors. First, we have the 3 connectors for the optical gyroscope, namely the X, Y, and Z axis connectors. These connectors take information from the gyroscope and sends it to the optical gyroscope ADC interface, which then sends it to board 6. Second, we have a similar X, Y, and Z axis connectors for the reaction wheel that conveys commands from port 6 to the wheel. We also have a small circuit that takes 5-volt input and acts as a power supply for wheel and the gyroscope through the aforementioned connectors.
With that, we'll present the current physical layouts for PCBs 1, 2, 6, and 9. Each set of red rectangles represents the copper padding for an electrical connection. The copper sits on precisely one side of a board where either a cable or an actual device will be mounted via some mechanical structure. The two 2x26 array of yellow hollow circles on the left represent drill holes for the PC104 stack. This allows for electrical connections to be made between components on different PCBs. The green shading, which covers most of the board, illustrates the grounding plane, which is essentially just a large single grounding point for all the devices. It's needed to shield against electromagnetic interference, which potentially distorts signals carried by copper traces. The holes located on each corner of the board allow physical mounting onto a chassis with the CubeSat and are plated for an extra ground connection. Here you'll see 3D models for the 6 printed circuit boards that we designed. Components are placed on the front and back to reduce the number of copper traces needed. Trace widths and spacing are determined by both the manufacturer requirements as well as our own determination of the amount of current each trace will carry. As you can see, the board is populated by both connectors, integrated circuit packages, and discrete components, all interconnected through a network of traces to realize our schematic designs. The 2 daughter boards shown here are mounted on each side of board 6 and carry an array of sensors which talk directly to the Arduinos. A common way for electronic projects to begin the testing phase is with a solderless breadboard prototype. While it's usually a suitable approach for everything but the most complicated and advanced designs, our project was somewhat constrained by the fact that many of our components were either proprietary, non-standard, surface-mounted, or simply operating in conditions we couldn't reproduce outside a lab. Because of these limitations, we were forced to do testing on systems using off-the-shelf substitutes operating at room temperature.
Once the Gerber files were complete for the PCB layouts, the last step was to organize these files and send them to our project supervisor Dr. George Zhu. As determined early in the project, our scope would not include the procurement of the final PCBs, rather just the Gerber files to be submitted to the designated manufacturer. Due to COVID restrictions, PCB testing was also beyond the scope of our project due to the delay in the manufacturing of the PCBs. However, any relevant documents including the testing protocols would be shared with the Essence Flatset testing team. We will now discuss some of the major lessons learned throughout this project. The first was to review interface requirement at every phase of the project. A NanoRex requirement was not accounted for, in which the 30-minute timer must be tested for on the ground, then reset before launch. This meant a modification to design at a later stage was carried out to allow the reset of the system. The next was to review specific component and protocols used to fully explore what changes to design is needed to account for these components. One prime example was the camera output. The signals were in a differential pair rather than in a single output. This meant the layout had to be redesigned so that the output traces were the same length and width and within the same proximity on the PCB. If this change didn't occur, the payload signal would have a higher chance of being interfered with and modified, distorting the collected data. The last lesson learned was related to scheduling. The team attempting to leave slack for the design and testing but failed to consider number of feedback iterations and the delay time between hearing back and to from the CSA. To account for this, the team tested in parallel with finalizing the design.
Team V is currently preparing all final documents and files, and is in discussion with the Essence team for the decommissioning of this project. Essence plans to complete the CubeSat assembly over the summer and complete testing by the fall of 2021. As a Capstone project, we successfully planned, designed, and tested 4 custom PCBs that will be integrated into the 3U CubeSat launching next year. Through this process, we learned the important elements of an engineering project, including background research, specifications, analysis, problem solving, testing, and communication. We'd like to thank the CSA, York University, the Capstone instructors, the Essence team, and all affiliated universities, companies, and personnel who made our Capstone project possible. Thank you for listening.